Hello everyone, welcome to this lecture on machine learning teach by doing. In this lecture, we will be learning about convolutional neural networks and their introduction. In particular, we have three agenda points in today's lecture. First, we will start out with the applications of convolutional neural networks. Second, we will look at the intuition behind why do we even study about convolutional neural nets and why not use just feed forward neural networks which we have looked at before. And thirdly, we will look at the history of development of convolutional neural nets. So, although this term has become really popular for the last decade, people have been working on this subject for the past 40 to 45 years, and it's very important to acknowledge their contributions. Convolutional neural networks are also referred to as CNNs. So, in this lecture, whenever I use the word CNN, I mean convolutional neural network. So, let's get started with the first section of today's lecture, which is the applications of CNNs. The first application which I want to show you is a simple cats and dogs image classification. So the interface which I'm showing you right now is called as teachable machine. What I have done here is I have uploaded 10 samples of cat images and I have uploaded 10 samples of dog images. And I have trained the model, and the final task of this trained model is that whatever image I upload as a test image, it should correctly classify whether it's a cat or whether it's a dog. It seems simple, but actually it's incredibly complicated to train an AI system or a computer to recognize images and what they represent. For example, look at this test image. The training image of all dogs are just from the front view and they are in different positions. Essentially, we are telling the uh, computer that I have given you 10 images of dogs. Try to identify patterns or features from these images which let you know that it's a dog. And based on these features, I'm going to give you some difficult test image and you have to do a good job on it. And the trained neural network here is doing an amazing job. Here, see, with 100% accuracy, it's saying a dog. And I think this is a difficult test image because it's shown from the side view and not front view, as are all the images in the training data. If I upload any other image, let's see how it performs. So now I'm going to upload the test image of a cat. And here also I'm going to upload a difficult image which was not part of the training data. With 100% accuracy, the trained neural network has predicted that it's a cat. In fact, this system or this model is so robust that any new image which you upload, cat or dog, it will correctly classify whether it's a cat or whether it's a dog. If you look at the second section here, the training, what's going underneath the hood is a convolutional neural network is trained. So the model which is making these predictions is not a simple feed forward neural network which we have seen before. It's a different type of a neural net which is called as a CNN or convolutional neural net. The second example which I want to show you is in the healthcare space, and it's called brain tumor detection. So imagine you have an MRI scan, and there can be two possible options based on the scan. A tumor is present, which means it's malignant, or a tumor is absent, which means it's benign. Of course, a doctor can take a look and manually say whether a tumor is present or not. But the question is, can we train an AI system to effectively look at an image and classify it as a benign or malignant, which means tumor is not present or tumor is present? So let's look at the data for this. We have data for malignant, and I'm going to show five images. Here you can see malignant images have bright white spots when tumor is present. And I'm going to also load the data for a benign. So here is one image, two. Here are five images of benign, which means that a tumor is not present and they look smoother compared to malignant, so they don't have spots. So humans can see this, but it's actually a very hard problem to train computers to look at millions of these images. And the task is that if I give you any new image, you should be able to correctly predict whether a brain tumor is present or not. This involves pattern detection. The computer or the AI should automatically detect uh, regions where a tumor is present and classify that as malignant. Now, if you look at the evaluation, let's do the model evaluation. Now, let's click on the second image and click on test the model. Here we can see that the model predicted benign and the actual value is benign. It's amazing, right? The trained neural network was able to correctly predict whether it's a benign tumor or malignant tumor just based on the training data set. Again, the underlying neural network architecture is not a feed forward neural network, but it's something called a convolutional neural network. Just take a look at this schematic. No need to worry about how it's working right now. I'm going to explain all those details in some of them in this video, some of them in subsequent videos. But remember the power of convolutional neural networks and what all it can achieve. The third example I want to show is a very interesting example called handwritten digit classification. So, let's say if you have written a handwritten digit, something like, let's say I'm drawing a 5 here, the computer converts it into a bunch of pixels, so it does not know it's 5. The task is to train the neural network so that any handwritten digit can be correctly classified. So, let's say I type 8 here. The neural network should be able to correctly predict based on the pixels that it's indeed an 8. If I type 3 here, the neural network should be able to predict that it's a 3. And it should do these predictions because some people type digits differently, right? I may type a 4 like this. I may even type a 4 like this. For both of these, the neural network should correctly predict it as 4. Similar to these applications which we just saw, convolutional neural networks have a wide range of applications. So, for example, if you take the example of self driving cars, how do these cars detect between objects, humans, and how do they make that distinction? There is a convolutional neural network which is trained underneath. Essentially, whenever you are dealing with images of some sort, a CNN or a convolutional neural network uh, operates underneath the hood. So I hope I have motivated you enough regarding the applications of CNN. But now let us try to look at a more deeper level regarding why CNNs are needed in the first place. So now we have come to the second example here, why convolutional neural networks are needed. So let's take a simple example of this cat, okay? And I have just drawn a schematic here and have roughly marked the position of this cat. Let's say that this is a RGB image, red, green, and blue, and it's 32 by 32 pixels in one channel. So the total number of pixels is 32 by 32 multiplied by 3. These are the total number of pixels in the input image, and that is 3072 pixels. Those are present in the input image. Why 3072? Because 32 into 32 for one channel, and we have three channels like these. So, a total of 3072 pixels. Now, let's say that I don't want to use a convolutional neural network, and I say that I'll just train a normal neural network based on this input. I'll just use a feed forward neural network. Let's see how that will proceed. So, in a feed forward neural network, you will need an input layer that will be these 3072 pixels. So, each input will have one unit here. So, there will be 3072 units in the input layer. And let's say that in the first hidden layer, we have 100 neurons. Now, every neuron here will have 3072 weights. So the total number of weights in the first layer itself is 3072 multiplied by 1000, which is around 300,000 weights. That is just in one layer. If we have 4 or 5 layers like this, it will lead to 1 million weights. This is not computationally efficient at all. In fact, it's extremely expensive computationally. And that's the first reason why feed forward neural networks are not used for image classification tasks. But this is a minor reason. There are two other major reasons why feed forward neural networks are not used for images. So let's look at image data, right? This data is very different than receiving data which these type of feed forward neural networks usually receive. They receive usually numbers such as the stock price, or if you take any other example such as the price of a given item on the particular day, and if you want to predict it for the next day, or if you see any classification task, binary classification, whether heart disease is present or not given certain metrics, so it mostly receives numbers as input. But when image is received as input, there are a lot of advantages of using image as data which feed forward neural networks do not exploit. In fact, there are two main advantages which are called spatial locality. That's the first advantage. And the second advantage is called as translational invariance. Let's see what both of these mean. Spatial locality means that the pixels of an image will always be close to each other, which means if I have an image of a cat, the pixels of the cat will always be close to each other, right? It will never happen that one ear the pixels are here and the pixels of the other ear are somewhere completely far, or the pixels of this eye and this eye are completely far from each other. In fact, if you look at all the pixels in the cat, they will all be close to each other. So that's the first advantage, and it's called as spatial locality. It sounds simple to think about right now, but it's one fundamental property of images that if you, let's say, locate the pixel of an eye, and if you look at the neighboring pixels, it's very likely that those belong to the cat and those are not external pixels. And that's a very important feature which we need to explore, or rather need to exploit when we deal with images as data. But feed forward neural networks do not deal with that at all. We just convert the pixels into a bunch of neurons, so all that information is lost. The information about space is lost. The information that this eye and this eye are close to each other is completely lost, since it just all pixels are converted into neurons. So that's one advantage, spatial locality. What these feed forward neural networks do is that they treat each pixel independently, and more importantly, it ignores spatial locality, and hence it is very difficult to capture patterns in the data. You need a huge training procedure, and it takes a huge amount of time to even correctly identify the patterns. But why do this if we can actually exploit the pixel dependence? Pixels of an image are close to each other and they're dependent on one another. So why don't we exploit it? For example, if you look at the outlines of a cat, it will be an edge, right? So it will probably be a light pixel transitioning to a dark pixel at the edge of an image. That is a spatial property, and such kind of features need to be exploited further. Okay. The second advantage of image as a data is something which is called as translational invariance. So the main point is that if this cat is here, or if shifted bit to the right, or if it's shifted bit to the left or top or down, it will still remain as a cat, right? It won't change into some completely different shape. But if you use a feed forward neural network, it lacks the ability to recognize objects irrespective of their positions, which means that even if we change the cat by a small amount, the cat position, all the activation functions will completely change. All the activations of the weights will completely change. The biases will change. So even small shifts in input image can lead to completely different activations. So we are not exploiting this property of translational invariance at all if we use feed forward neural networks. It also sounds simple, but it's a very fundamental property, right? Let's say if the cat shifts in any small direction, it will still remain a cat. So the architecture which we have should be robust to translational invariance. Even if the image moves a bit, we should not change too much the parameters of our architecture, and it should still be able to recognize the image present. Convolutional neural networks satisfy both of these advantages of image as a data. First, CNNs leverage spatial structure by using something called as convolutions or filters. We will use the term filters a lot throughout uh, this lecture and also next lectures. And this term is interchangeably used with filters or kernels. So CNN leverage spatial structure by using convolutions. Convolution is a mathematical operation, but it's much easier to understand convolutions if we understand filters. And what filters do is that they help us to capture edges, textures, and shapes. So let me give you a simple example of what a filter actually means. The simplest way to think of a filter is looking at Instagram filters. If we apply a filter, let's say a blur filter on Instagram, the photo will get blurred. If we apply a night filter, all the pixels will change, right? So essentially, you can think of filters as capturing some kind of a detail in that image. To illustrate that property further, let us look at an interactive demonstration of what filters can do. So let's say that I have a blur filter which takes in this image and then it will blur as the output. So look at the left image and I will apply the blur feature here. So let's say I'm sliding the I'm sliding the filter on the left image and look at the output on the right image. The pixels are getting blurred, right? Which means that whenever you apply a filter on this particular image on the left hand side, every filter has an action which reflects on the right hand side. So this is the blur filter. If you look at the outline filter, for example, look at what's happening here. So if I want to capture the outlines of a particular image, so let's say if I want to capture the outline of this cat image, somehow my neural network should recognize that this outline filter should be applied somewhere, right? And if you think of this filter operation left to right, left and right image, we can see that things are changing, but in the middle you can see that every filter is represented by a set of mathematical numbers, and these are the numbers which will be treated as weights. So in feed forward neural network we have neurons, right, which we optimize. In convolutional neural network we will optimize the numbers in these filters, and they will be optimized so that every filter which we use will capture something new. Let's say one filter will capture edges of the cat, one filter will capture any isolated pixels of the cat, etc. And every filter can have different functions, as we are seeing here. The blur filter here blurs the image. The outline filter, the outline filter here captures the outline. The sharpen filter here sharpens the image a bit. So essentially, every filter has a specific application. So convolutional neural network deal with filters, which means that instead of optimizing weights of a neural network, we try to detect which filters can be used so that we detect all the patterns in this image. And that is how spatial locality is exploited in convolutional neural networks. For example, look at this interactive demonstration. This is how convolutional neural networks actually look like. You can see that they have layers similar to a feed forward neural network, but every layer filters are applied. So let's look at the here you can see the image of a teacup, right? And it's decomposed into three channels: red, green, and blue. And this image passes through layers of a neural network. In the first layer, you can see that there are different filters: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these 10 weights you don't think of as neurons now, think of them as 10 filters. So when you click on the first filter, you can see that a filtering operation is applied, right? Similarly, when you click on the second filter, the different filtering operation might be applied. So you can think of these 10 filters as every filter is trying to learn something new. So in the first layer of this convolutional neural network, we are maybe detecting broad features such as outlines, etc. Now, as we move to the second layer, again we can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There are 10 filters here. There are 10 filters here, and each filter here might detect some complicated features, more complicated than the first layer. And as we go deeper into the neural network, patterns are detected more and more. So, more and more detailed features are detected by the filters. So, maybe as we go deeper into the neural network, we detect that there is a curved handle here, and there is a curvature which resembles like a cup. So, you can think of as each layer comprising of filters, and every filter essentially learning something new. When we reach the final layer, we have to make the prediction between lifeboat, ladybug, pizza, bell pepper, school bus, etc. And we can see that the maximum prediction is for the espresso, which means our convolutional neural network is correctly identified the input image as that of an espresso. We will go into detail of exactly how these layers have been constructed. You will see there is a ReLU operation here. There is also max pool. Why are they needed? We'll go into detail. But I just want to show you that convolutional neural networks do look like neural networks, but instead of neurons, we have filter operations which are applied in every layer. And each filter operation detects something new. As we go deeper and deeper, more intricate patterns are detected. So let's say you're detecting a zebra. Maybe in the first layer, edges are detected, contours are detected, and then in one of the middle layers, black and white stripes might be detected as a more advanced feature. And then finally, we detect that it's a zebra. So this is how convolutional neural networks leverage spatial locality through filters, and we'll learn about them. And CNNs also leverage translational invariance. So they use techniques like pooling layers and shared weights. So here you can see that there is something called a max pool. These techniques ensure that even if the image is shifted slightly, our learned weights will not change too much. So convolutional neural networks are robust to image translation. So the reason CNNs are used is because they exploit two features of image as a data, spatial locality and translational invariance, which feed forward neural network just do not exploit. So now, as you can see, we have covered the second section of CNNs. Now let's come to the last section of this lecture, which is history of convolutional neural networks. It is very important to acknowledge that this field has history dating back to 45 years, and we should acknowledge the different contributions. So the first CNN architecture was introduced in 1980. This is the paper which was called Neocognitron, a self-organizing neural network model for a mechanism of pattern recognition, unaffected by shift in position. See, this is translational invariance. In fact, this paper exploited both of these properties, spatial locality and translational invariance, and they proposed a CNN architecture which looked like this. Here, you see, it does look like modern CNN architecture. So, in the brain tumor, what I showed you, this architecture looks very similar to what has been proposed in the paper. However, this was in 1980, and they did not use backpropagation also. They used a simple algorithm which belong to unsupervised learning. They did not use the supervised learning algorithm here, and that's why this method is not efficient in modern times. It turns out supervised learning is the best way to train CNNs. So that's why neocognitron is not used currently, but it's important to acknowledge that this was the first CNN. A real big breakthrough in CNNs happened in 1989 through this paper which introduced the LearnNet. Now, LearnNet also had these properties of spatial locality and translational invariance, but apart from that, it used the backpropagation algorithm, which was introduced quite recently, and it trained the weights of the neural network through a supervised learning approach. Here is the paper for that. It's called gradient based learning applied to document recognition. So the only drawback was that they used small amount of layers. So the architecture was not very deep, and it was not trained on millions of images like it is done today. But it was still looking like the modern architecture which I showed you here. So this paper was also great, and it was a milestone in convolutional neural networks. And the further breakthrough came in 2012 when the AlexNet paper was introduced. This paper won an ImageNet challenge by a huge amount. And the difference between this paper and the LearnNet was that this paper was trained on a huge amount of data, and they used a larger CNN. They also used different techniques like dropout technique, etc. A number of modern machine learning techniques were used in this paper. So typically, all CNN architectures which you see right now are variants of this AlexNet paper which was published in 2012. Let me actually get that paper for you. So AlexNet paper 2012. You can see this paper has 130,000 citations now, and it's just a 9-page paper, but it was extremely impactful when it was released. So, this is the history of convolutional neural networks. I hope you appreciate the 45-year work which people have done in this field. Okay, so just to summarize, in today's lecture, we covered three parts. We covered the applications of convolutional neural networks, why CNNs are needed, and then we also covered the history of CNNs. In the subsequent lectures, we'll be looking at filters, we'll be looking at the CNN layers, how the filters are optimized, how the filters are trained on images, etc. So, thank you so much, everyone, and I look forward to seeing you in the next lecture.